So our next topic is series, infinite series. Now a series is an infinite sum of the form a1 plus a2 plus a3 plus indefinitely. We use the summation notation that we have seen before in when we talked about the Riemann sum. So we've seen this summation, but here the summation is to infinity. So it's an infinite sum. And a1, a2, a3 represent a terms of some sequence. Now the sum of the first n terms is called the nth partial sum. So usually we denote it by Sn. So Sn is a1 plus a2 up to an. The sum of the first n terms. This is called the nth partial sum. Now if you look at the partial sums, like S1 for example is a1, S2 is a1 plus a2, and so on. Sn is a1 plus a2 up to an. The S1, S2, S3, Sn, they form also a sequence. Okay, the partial sums themselves are sequences, are a sequence of the sum of the sequence a1 through an. Now if we take this partial sum, so suppose that I have Sn, remember that Sn is equal to a1 plus a2 plus an, and we have generated these sequences Sn's. And let's say that I'm looking for S, capital S in this case is going to be the following: the summation from k equals 0 or from n equals 0 to infinity of these numbers an. Okay, so if you let this Sn, if this Sn goes to infinity, okay, when n goes to infinity, sorry, this is gonna approach some limit S. Now if this limit S is a number, then we say that the series converges. Okay, if not, then we say that the series diverges. So you see here the S is the limit of this sum a1 plus a2 plus an, and let's say that you are able to find the limit of S. That means the value of S that you got here is actually the sum from n equals 0 to infinity, actually not n equal 1 here, to infinity of an. So this is like you are getting a value for an infinite sum of numbers if it's convergent. Otherwise, then S is going to be infinity. Now, finding this S is very hard sometimes because finding a formula for Sn is not obvious. Not every time you can give me numbers a1, a2, an, and then I try to say, well, Sn equal a1 plus a2 plus etc. plus an. I need this to give me a nice formula. And that's not always the case. And most of the times I don't have this nice formula, because if I do, then working with series will be very simple. It's like the same as working with sequences. But the problem here is that you don't always have this case. We do have it for some special cases that we will discuss. Okay, the first case that we will discuss here is called the geometric series, and this is related to the geometric sequence. A geometric series is a series of the following form: summation from n equal 1 to infinity r to the power n minus 1. So if you expand this, you're gonna get the following expanding. The nth partial sum Sn, so again remember Sn here means a1 plus a2 plus an. So basically Sn is really 1, actually I have an a here, so that's a times a plus a times r plus a times r squared up to a times r to the power n minus 1. Okay, because when these are n terms, because I'm starting this like r0. Okay. So this Sn has a nice formula. The nth partial sum is Sn equal a times 1 minus r to the power n over 1 minus r. So now working with a geometric series is not hard, because if I have a series, then I can express the nth partial sum, and then I will know that S, which is the sum from n equal 1 to infinity, we can ignore the a, because you know the a I can move outside, so the a is a constant, I can ignore it. So here, when r is less than 1, we have mentioned in this when we talked about sequences that r to the power n goes to 0 when absolute value of r is less than 1. Okay, so what does it mean here? That means if I take this limit, if I let n goes to infinity and I take this limit, then I'm gonna get a, well, times 1 minus 0 over 1 minus r. So basically a over 1 minus r. If I don't have the a, then it's gonna be just 1 over 1 minus r. And this is what's happening here. So now, every time, and this is very important, the series will converge if and only if absolute value of r is less than 1. Moreover, I will be able to find the sum of the series. That means if you add all the numbers of the form r to the power n minus 1 from n equal 1 to infinity, my answer will be 1 over 1 minus r. If r is greater or equal to 1, then the series is gonna diverge. Okay, so it will only converge if r is absolute value of r is less than 1. It could be negative as long as it's between minus 1 and 1. Okay, I'll show you now an example about this. Consider the following series. First, this is geometric because this can be written as summation from k equals 0 to n 1/2 to the power k. So this is my the r here. R is equal 1/2. Okay. Now one thing I want you to be careful about. I want to find the sum of these numbers. Okay. But this is not the one that I had in the previous slide. Remember, in the previous slide, Sn, I wrote Sn to be the sum of the first n terms. Now the first term is a times r to the power 0. The second term is a times r, and so on. So the nth term will be a times r to the power n minus 1. So I have to be very careful here, because what I have in front of me right here is actually a times 1 minus r to the power n over 1 minus r. So I can only use the formula, okay, if I have this sum. Okay, so I'm talking about the following. If you want, I can give you a better expression for Sn. Sn can be written as summation from k equal 1 to n a times r to the power k minus 1. So the last term is when k is equal to n, and that's going to give me a to the power r n minus 1. The first term is when k is equal to 1, and that's going to give me r to the power 0, so just a, and as you can see here. Okay, so to use this formula, I need to have this sum. It starts at 1, finishes at n, and the power of r is k minus 1. In the example I have here, this is not exactly the same. Okay, because this is written in the following form: k equals 0 to n 1/2 to the power k. So I need to make it look like the one that I had. To make it look like the one that I had, first remember that this sum is actually summation from k equal 1 to n of 1/2 to the power k. Now someone will say, what happens to k equals 0? Well, I will add it by itself, plus 1/2 to the power 0. Now 1/2 to the power 0 is this one that you see here. And over here, it's the sum from k equal 1 to n of 1/2 to the power k. Okay, I still cannot use my formula properly, because remember, my formula was this summation. It was the sum from n equal 1 or k equal 1 I had in the previous slide. K equal 1 to n, a multiplied by r to the power k minus 1 this is what gives me a times 1 minus r to the power n over 1 minus r. Okay, so I want to have this form so I can apply the formula. Till now, I don't have this form. Okay, but I can do something here. I can make it look like this. The only thing I'm missing is I need this to be to the power k minus 1. So this can be written as summation k equal 1 to n 1/2 by itself and another 1/2 to the power k minus 1. Now this is gonna work. My a is equal to 1/2 and my r value is equal to 1/2 as well. So the 1, I carry the 1, that's a right here. So this is the a, which is 1/2 times 1 minus r to the power n. So it's 1/2 to the power n over 1 minus 1/2. So this is 1 minus 1/2, which is equal to 1/2. It's going to cancel with this 1/2. So what's left is the 1 that I have here plus 1 minus 1 over 2 to the power n. We know that 1 over 2 to the power n goes to 0 as n approaches infinity. So now Sn, or the value of this when n goes to infinity, is equal to 2. It's 1 plus 1. So when n goes to infinity, that's going to be 1 plus 1 minus 0. Another example, is the series convergent or divergent? So far, we have only seen one type of series, which is the geometric series. And the geometric series looks like this. Keep in mind, it's sum from n equal 1 to infinity a times r to the power n minus 1. And if r is less than 1 in terms of absolute value, then it's convergent. If r is greater or equal to 1, then it's divergent. Okay, so I have in front of me a sequence. Well, the sequence term is 2 to the power 2n multiplied by 3 to the power 1 minus n. What I want to do here actually is I'm going to try to write this in this form. I think we should be able to make it because I'm taking the product of two exponentials. Okay, so I start by doing the following. This is the sum. I mean, n equal 1 to infinity, it's good. I don't need to change anything here. This can be written as 2 square to the power n. Okay, and this can be written as 1 over 3 to the power n minus 1. So basically, this is the sum from n equal 1 to infinity, 4 to the power n over 3 to the power n minus 1. Well, this is good. This is good so far because I'm getting close to what I need. I only need to have the power n minus 1, not n. So for 4 to the power n, I can write it as 4 times 4 to the n minus 1. So this becomes summation from n equal 1 to infinity, 4 multiplied by 4 to the n minus 1 over 3 to the n minus 1, which is the sum from n equal 1 to infinity, 4 times 4 over 3 to the n minus 1. So it is a geometric series. The value of a is equal to 4. The value of r is equal to 4 over 3. However, it's easy to see that r is bigger than 1. And once r is bigger than 1, then I can conclude that the series is divergent by the theorem that we have stated earlier about the convergence series. So this is divergent. Okay, because the ratio r is bigger than 1. Okay, one more example of this type. This is the complete solution here. Suppose that I have the sum from n equals 0 to infinity, 2 over 3 to the power n plus 2. Show that the series is convergent and I want to find its sum. Again, I want to write, look, some books, they have the formula started at 0. Our book, they use the formula starting from 1 to infinity. So I'm just going to use this formula. A times r to the n minus 1. So I want to make it look like this. So I can do the following. I can consider the case when it's equal to 0. and then I can start my sum from n equal 1 to infinity. 2 over 3 to the power n plus 2. Now, this is going to be 2 over 3 to the power of 2 plus summation from n equal 1 to infinity. Over here, I want to create something like a times r to the power n minus 1. I have 2 over 3 to the power n plus 2, so I make it 2 over 3 to the power n minus 1. And what's left is 2 over 3 to the power 3. I'm just trying to split this using the properties of exponents. So now I have 2 over 3 square plus summation from n equal 1 to infinity. This is 8 over 27. Okay, so this is the value of a multiplied by 2 over 3 to the power n minus 1. So this is this looks exactly like the one that I have. This is a, this is r. R is equal to 2 over 3, which is less than 1. Okay, so this means the following. This means that the series is convergent. Moreover, we know the value of the sum. So I can move this outside if I want. So this is equal to 4 over 9 plus 8 over 27 multiplied. The sum from n equal 1 to infinity, r to the power n minus 1 is 1 over 1 minus r. And this is gonna give me 4 over 3. You can check the calculation and you can see it done right here. Okay, so if we have a geometric series, then it's good news. I can tell easily just by doing some algebra to write it in the appropriate form. I can tell whether it's convergent or divergent, and if it's convergent, I can find its sum, and I cannot do this for any series. So this is a very special kind of series. Another type of series that we will talk about is called telescoping series. Look at the sum I have here in front of you. I'm claiming that this sum is equal to 1. It's not geometric. Okay, it's not geometric. I'm just adding. So if I want to write this, this is like the summation of 1 over k multiplied by k plus 1 from k equal 1 to infinity. I'm adding this sum. That's an infinite sum. It's not geometric at all. But how do we know, or how can we find that this is equal to 1? Well, here's the trick. It's like we use partial fractions here actually. So if you use partial fraction, you can see that 1 over n times n plus 1 can be written as 1 over n minus 1 over n plus 1. Okay. Now this is good news. Why this is good news? Because you know, if I want to write the partial sum Sn, which is up to this point, so this is Sn up to here, then what happens is instead of 1 over 1 half, instead of each fraction of this form, I can write it in that form. That means 1 over 1 times 2 is 1 over 1 minus 1 over 2. 1 over 2 times 3, it's 1 over 2 minus 1 over 3. 1 over 3 times 4, it's 1 over 3 minus 1 over 4 till the end. Okay. Remember, if you want to add a term that comes right before this, it's going to be 1 over n minus 1 plus, or sorry, minus 1 over n. Okay. And things going to keep going. So we're going to stop up to s, up to n, because this is Sn. Now I want you to note something. Look, minus 1 half cancels with 1 half. Minus 1/3 cancels with 1/3. Minus 1/4 cancels with the 1/4 that will come here. I have a minus 1 over n that comes before this is going to cancel with this. So everything is going to cancel except this guy doesn't cancel and this guy doesn't cancel. So this is my answer. This is what? This is Sn. This is the nth partial sum. Okay. Now I can take the limit of this. And when I take the limit of this, I'm gonna get s. So this is the which is the sum that you see on the top. So this type of sum is called telescoping. Okay, because what happens is that the whole sum collapses like a telescope to just two terms, sometimes more than two terms. Okay, it depends on the problem that we have, but to few terms if I want to say it. So this s is actually the limit of the partial sum. This is the series. It's the sum. It's the limit of the partial sum Sn when n approaches infinity. So this is the infinite sum. It's calculated by taking the limit when n goes to infinity of the nth partial sum. Now the nth partial sum, as we saw in the previous slide, this gets simplified to this nice terms 1 minus 1 over n plus 1. When n goes to infinity, this is going to be 1 minus 0, which is 1. And that's why we were able to do this. We were able to have the sum equal to 1 at the beginning. I'll show you another example. Determine whether the series summation from n equal 1 to infinity ln of n over n plus 1 converges or diverges. If it converges, find its sum. Okay, so here's what I'm going to do. I'm going to consider the nth partial sum, Sn. Okay, so this is the sum from k equal 1 to n ln of k over k plus 1. And I want to use the properties of logarithm to write this as ln k minus ln of k plus 1. Okay, now I want to write explicitly the meaning of this sum. This really means the following. This is ln of 1 minus ln of 2 plus ln of 2 minus ln of 3 plus ln of 3 minus ln of 4. I hope that you are seeing the pattern now. This is going to keep going. Let me write the last two terms. When when k is n minus 1, I get ln of n minus 1 minus ln of n minus 1 plus 1, which is ln of n. Plus the last term, when k is equal to n, I get ln of n minus ln of n plus 1. Okay. Notice that this is a telescoping series. Okay, because what's happening here is some terms will cancel. Minus ln2 cancels with plus ln2. Minus ln3 cancels with ln3. Minus ln4, there's an ln4 here, will cancel. This is going to cancel with the previous one. Minus lnn cancel with lnn. So I have a nice formula for Sn. This implies that the partial sum Sn is equal to ln of 1, which is 0. What's left is negative ln of n plus 1. Now, S, which is the sum that I have, this infinite sum is S, is just the limit of the partial sum Sn when n approaches infinity. This means it's the limit when n approaches infinity, negative ln of n plus 1. And this is going to be negative infinity because when n gets large, ln of n gets large as well. And because I have a minus, that's negative infinity. So as a result, s is equal to negative infinity. This means the series is divergent. Okay. Now, as we have properties for limits, for derivatives, for integrals, we have seen also for sequences properties, we do have properties for the infinite sum, for series. Okay, but to be able to do this, I need to know that the series are convergent. So suppose that I have two different sums, a sum A and sum B, where A is the sum from k equal 1 to infinity of some AKs, and capital B equals sum from k equal 1 to infinity of some BKs. And assuming that both are convergent, then if you have the infinite sum of AK plus BK, you can split this. Okay, you can split this, and then instead of doing so my answer is going to be a plus b. The reason is very simple, because when you split this, you can rearrange the terms here. So you can make a1 and a2, a3 together, and then you can make the b1, b2, b3 together. So this is going to give you the sum of a plus the sum of b. So this is the idea here. Also, if there is a constant multiplied by the sequence inside, then you can move the constant outside. So you can move any constant, you can move it outside of the series, of the summation. Okay. So just regarding how you get from here to here, I have it right here. So that's what I was talking about, that you can just rearrange the sum so that the ai's together, this is the sum of ak, k equal 1 to infinity, plus this is the sum of bk, k equal 1 to infinity. Now here we have a really nice theorem, one of the most useful theorems. Its equivalent, as you will see, is one of the most useful theorems in this topic. If sum from n equal 1 to infinity of an converges, so if the series is convergent, then automatically we should conclude that the sequence, the sum, I mean, when you have a series, you are adding sequences. So that sequence will go to 0 when n approaches infinity. The proof is nice and simple. So let's take a look at the proof. First, we consider the nth partial sum. So this is Sn. If you look at Sn plus 1, that's going to be the sum from k equal 1 to n plus 1, ak, same thing. So if you take the difference, Sn plus 1 minus Sn, okay, you're gonna get actually you're gonna get An plus 1, not An. Okay, I mean that's fine. Then what happens is, so this is, as I said, it's gonna be n plus 1. What happens is we're gonna take the limit when n goes to infinity of this, of Sn plus 1 minus Sn. Now, because we are assuming that this is convergent, that means this is equal to some letter s, some number s. So limit when n goes to infinity of this is the same, because it's like, it's wrong to write it, but you think about it in this form. This is like s infinity minus s infinity. What happens to s infinity, which means infinity plus 1 is the same, it's infinity. So the answer is going to be s minus s here. Okay, because if limit of Sn when n goes to infinity is s, it's going to be the same as doing limit of Sn plus 1 or Sn plus 2 or even Sn plus million or even Sn minus million when n goes to infinity, because it's like having s sub infinity, so it's the same thing. So this is going to be equal to the limit when n goes to infinity of An plus 1. Now this is going to be 0, so the limit of An will be 0. Now if An goes to 0 when n goes to infinity, it's the same as if An plus 1 goes to 0 when n goes to infinity. Okay. But you know, this theorem, if you just take a look at this theorem in this format, it's not useful at all, because it's easy for us to know whether the limit of the sequence is equal to 0 or not. Taking the limit is much easier than telling whether a series is convergent or no. So my goal is actually to know if the series is convergent. So this doesn't help me if it's written in this format. However, this theorem can be helpful if we consider its contrapositive. Okay, remember the contrapositive. Like if you have a statement P implies Q, okay, its contrapositive is of the form not Q implies not P. This is going to be very important. And actually we have this is called the divergence test. Here's what we have here. So an important consequence of this fact is its contrapositive, which can be stated as a theorem. So as I said, it's not P not q implies not p. Not q means limit of an is not equal to 0. Not p means sum of an diverge. So this is called the divergence test. This tells you the following. It's telling you that if limit of an is not equal to 0, then the sum from n equal infinity to an is divergent automatically. Okay, but you have to be very careful. The converse is not true. So that means if limit if the limit, or if the sum of an from n equal 1 to infinity diverges, okay, this does not mean that an does not go to 0 when n goes to infinity. Okay, this doesn't mean this. Also, if an goes to 0, this does not imply that sum of an converges. Okay, we're gonna see examples that will show you that that's not true. In fact, this is a very famous one. We will talk about it in a different video. Sum of 1 equal n from n equal 1 to infinity. This is a sequence. This is a series. This is an. An goes to 0 when n goes to infinity. But this series is not convergent. This is divergent. It's called harmonic series. We will talk about it later. So it's important to note that the converse of this theorem, of the theorem above, is not true. Okay. But here's how this theorem can be useful. Determine whether the series is convergent or divergent. If it's convergent, find its sum. Now look, so far you haven't learned many things. You only know the following. You know the geometric, you know telescoping, and you know the divergence test. So let's take a look at this. This is an. Let's find limit of an when n goes to infinity. This is the limit when n goes to infinity of 2 plus n over 1 minus 2n. We have found these limits when we talked about sequences. This is like a rational function. So this is going to be 1 over minus 2, which is not equal to 0. Then, by the divergence test, the one that we stated in the previous slide, then by the divergence test, the series diverges. So look, if you get limit equal to 0, you cannot say anything. So the test is inconclusive. But if the limit is not equal to 0, then you can conclude directly that the series is divergent. Okay. Here, for the second example, actually this is not, I don't need to use the divergence test here because I can see that this is geometric. Okay, I can see that this is a geometric series. Actually, it's a sum of two geometric series. This can be written as follows. This is the sum from n equal 1 to infinity. Because I know that this is geometric, and moreover, I know that the ratio here is going to be negative 0.2. The ratio here is going to be 0.7. Here it's between negative 1 and 1, and similarly here it's between negative 1 and 1. So I know that it's going to be convergent. And because I know that the series are convergent, I can split the sum. So this is the sum plus sum. So I'm using the properties of, but I wanted to see this very good here because when I was able to split this sum, this infinite sum, I was able to split the infinite sum because I knew that these are geometric series that are convergent. That's why I was able to do it. Now I need to find the sum. This can be applied directly, 0.7 to the power n minus 1. Here maybe I need to just write it in a different way. So I can write it like this. negative 0.2 to the power 3 multiplied by negative 0.2 to the power n minus 1 plus summation from n equal 1 to infinity 0.7 to the power n minus 1. Then I can apply the formula. Okay, remember that the formula that we were given, that we had for the geometric series is sum from n. So let me just write it here again. Sum from n equal 1 to infinity Rn. If R is between negative 1 and 1, Rn minus 1 here is equal to 1 over 1 minus R. So I will just need to apply this formula to be able to find the sum. So this is equal to, I can move negative 0.2 outside, negative 0.2 to the power 3, I can move this outside, so this is negative 0.2 to the power 3 multiplied by 1 over 1 minus negative 0.2 plus, here I don't have any constant to move outside, so this is just 1 over 1 minus 0.7. So you can see that this can be found and you get a number which is the sum for this series. So clearly the series is convergent, and that's what we expected from the beginning. Here another exercise that I recommend you try, and then you can ask me if you have any questions. This is, try it, it's telescoping. See how you can use partial fractions to decompose it. This is telescoping, and this is telescoping as well. These two are telescoping. In both of them, you can, I recommend you write the partial sum, try to see what's canceling out and what's left. So try to find a formula for Sn and then take the limit when n approaches infinity.